So good morning, students. I welcome you all to this first lecture on linear algebra. So am I audible to you, and is the screen clear to you? Jen, no, my PhD is not in mathematics. Okay, I am from mechanical background. Okay, so yeah, I hope things are going fine. So see here. So this linear algebra is common to all the branches in Gate. So we'll see why to study linear algebra first. Could some of you suggest me why to study linear algebra? Any one of you? Please don't tell me to get 2 to 3 marks in GATE exam, okay? We have something big than that. So why do we need to learn linear algebra? No responses for quantum mechanics. Okay. Next, to solve when we need to solve 2 or more unknowns. Okay. Simplification for coding, solving system of equations. Correct. Yeah, many of you are probably correct. So see here. Let me write the things. Generally, when we encounter some system of equations, some linear equations, basically, for example, let me change this. Okay. So when you encounter such equations, b1y is equal to c1, a2x plus b2y plus c2 is equal to, is equal to c2, such kind of equations. Normally, when the unknowns and equations are very small in number, so that you can perform mathematical operations and you can get the values, it's easy. But when number of unknowns and number of equations gets increased, number of operations required to perform this, to get the values of these variables is really tough. Okay, so matrices help us generally to solve system of equations. Okay, and also we have this matrices also tells us some good important points about there's something called ill-conditioned equations, which I deal in numerical methods course, numerical methods chapter. But right now, I want to tell you this matrices really play a very important role in engineering mathematics. And also, if you deal with multi-dimensional vibrations and all these things, this linear algebra, basically these matrices have a really big impact or importance in the course, and will study the syllabus that is in GATE examination in this particular course. Okay, so linear algebra, look. So straight away, we'll start our discussion with the definition of a matrix. So tell me, what is a matrix, all of you? See, this is, a bit easier topic, but not too much, a bit comparatively when compared to other topics. So what is a matrix, all of you? If someone know, please tell that. What is a matrix? Arrange the elements in rows and columns. Okay, so any array, in the sense arrangement of elements in horizontal lines. In horizontal lines called rows and vertical lines called columns is called a matrix. Okay, yeah, correct. I got many definitions. Combination of elements in row and column. Okay, m by n rows and columns. Okay, fine. Yeah, all of you are correct in some sense. So examples, if you see, for example, 2, 3, 4, we arrange this 2, 3, 4 in a horizontal way, and 4, 5, 6, for example. So we say these horizontal lines as rows and these vertical lines as columns. So if you see, this matrix has 2 rows and 3 columns. Okay, so order or size of the matrix. Size of the matrix. Okay, so if a matrix capital A, generally matrices are denoted by capital letters. So if a matrix capital A has m rows and and n columns, then we say that the matrix is of size, the matrix is of size m cross n. You should read this as m by n. You should read as m by n. See, don't feel that by writing these small definitions, matrices is very easy. I want to start from the basics because a few people at the beginning of this mathematics course, they have asked me to discuss from the basics, so I am dealing all these things. Okay, so please don't take lenience of that and don't feel this matrices is very easy. Okay, I'll prove you wrong if you feel such. Look. Okay, so for example, if you see the size of this matrix, for example, if you come back here, example, A is equal to, same matrix, let us take 2, 3, 4 and 4, 5, 6. Then A is a matrix of order 2 by 3. Correct? Because if you see, we have 2 horizontal lines, basically 2 rows and 3 columns. So if you have m rows and n columns, you call that as m by n. So here we have 2 rows and 3 columns, so we call that as 2 by 3. Okay. So next, equality of matrices means if 2 matrices are to be equal, what's the case? Okay. Equality of matrices. Two matrices A comma B are said to be equal. You can't compare two matrices. Okay, you can't say which matrix is, having more or less. You can't write A greater than B or A less than B, but you can say A is not equal. A is equal to B or A is not equal to B. That's it. Okay, are said to be equal if first one, order of A is equal to order of B, and 2 corresponding elements must be equal in both the matrices. Corresponding elements should be equal in both the matrices. Okay. So generally, for writing a matrix, you need not completely define the matrix. It's enough if you define, a format for that. For example, A is equal to 2, 3, 4, then 3, 4, 5 can be represented as, this matrix is same as A is equal to Aij, where Aij is equal to I plus j for all 1 less than or equal to I less than or equal to 2, 1 less than or equal to j less than or equal to 3. See, look, this is a bit near form to some of you. So see here, any matrix can be represented in this form by specifying one element in terms of row number and the column number. See here, this matrix is a matrix of size 2 by 3. Correct? So if you see this Aij denotes element in ith and jth column. Okay, so if you see, for example, if I talk about this element which is here, this is in the first row and in the second column. So the value of I for this corresponding element 3 is I value is 1 and j value is 2. So if you see, if I want to calculate A12 element, means element in the first row and in the second column, then Aij is given by I plus j. So 1 plus 2 is equal to 3, and you will be getting this element. Okay, so likewise, instead of writing complete matrix, because many times it's not possible for us to write the complete elements of the matrix, so in such cases we'll define the matrix in this format. We'll define some mathematical operation in terms of I and j for this element aij. Okay, so this is the case. Now if you want to say that A and B are two matrices to be equal, you can write for the matrices A m by n and B p by q to be equal. First case is their order should be same, which means m is equal to p and n is equal to q. Next, corresponding elements must be same, means aij is equal to bij for all 1 less than or equal to I less than or equal to p and 1 less than or equal to j less than or equal to q. You can replace with m and n as well, because p is same as m and q is same as n. So first of all, their size should be same, as we have seen. Like, you know, if I give an example for you, A is equal to, let us take a simple case of 2 by 2, A, B, C, D, and B is equal to, for example, 1, 2, 3, 4. Then if I say that these two matrices are equal, then definitely this is of size 2 by 2 and this is also of size 2 by 2. So if you see, for these two matrices to be equal, for A equal to B, size of these two matrices should be equal. Yeah, 2 is equal to 2 and this 2 is also same as this 2, so it's fine. Now elements, respective elements should be same. So A value is equal to 1, B value is equal to 2, C value is equal to 3 and D value is equal to 4. Okay, so these are different, you know, two conditions that have to be held by these two matrices for the equality of these two matrices. Okay, so next, see here. Now we'll look at types of matrices, which is really important in GATE examination because they'll ask you for a lot of questions based on this. Types of matrices. So first one, square matrix. Now tell me, what is a square matrix? What is a square matrix? All of you, please tell me what is a square matrix. M is equal to n. Okay, so a matrix A is equal to Aij m by n is said to be a square matrix. Is said to be a square matrix if m is equal to n. Means number of rows should be equal to number of columns basically. Examples, you can write A is equal to some 3 by 3 matrix, anything that you wish. Yes, correct. M is equal to n. Matrix of order n by n, m is equal to n, correct. Yes, correct. Number of rows is equal to number of columns, correct. So basically m should be equal to n, means if you are denoting this with rows and n with number of columns, both of them should be same. So that's the case. So let us take a simple case of some 3 by 3. So you can write 1 4 3 3 4 1 4 1 3. Okay, so anything of these numbers, basically number of rows should be equal to number of columns. That's the only thing. So next, upper triangular matrix. Upper triangular matrix. Now what is an upper triangular matrix, all of you? See, I'm asking you this because you have different types of matrices. So if you keep telling, you will get familiar with these types. Okay, so please tell me, what is an upper triangular matrix? Elements below the principal diagonal are 0, correct? Yes or no, all of you? Yeah, elements above principal diagonal, what are they, Anil? Like they should be 0 or less than 0? Yes. Elements below the diagonal are 0. So see here, a matrix capital A is equal to Aij n by n is said to be an upper triangular matrix, an upper triangular matrix if Aij is equal to 0 for all I greater than j. Yes or no? Because if I is greater than j, the element falls below the principal diagonal. Meanwhile, if someone don't know what is the principal diagonal, then this is the principal diagonal of the matrix, which consists of all the elements with Aij, where I is equal to j. So if you see this element, this is A11, A22, A33. So I value is equal to j, and the diagonal that connects all these elements in which I value is equal to j is called the principal diagonal. Okay. So now if you see this particular condition, Aij is equal to 0 for all I greater than j, you can write a normal definition. A matrix A is said to be upper triangular. A is said to be upper triangular if all lower diagonal elements are 0. If all lower diagonal elements are 0. Okay, so this is the case. Both actually denote the same thing, because see, if you have this element A is equal to A11, A12, A13, A21, A22, A23, A31, A32 and A33. So if this is the case, then this is the principal diagonal corresponding to this matrix, correct? If this is the principal diagonal, then for this, okay, you want some time to it? Yes, it is in syllabus for all branches, Lokesh. So see here, A11, A22 and A33. So now if this is the case, lower diagonal elements are these elements, correct? Now all these three elements, A21, A31 and A32 should be 0. So if you see, in every element, this I value, which is the row number, is greater than the column number. Okay, so therefore for A to be upper diagonal, matrix, Aij is equal to 0 for all I greater than j. Okay, I'll give you some time to write, no issues, you can take. Next, okay, taken. Next definition is lower triangular matrix. Define what is a lower triangular matrix. See, I have defined what is an upper triangular matrix, correct? Now you define what is an lower triangular matrix. Aij is equal to 0 for all j greater than I or I less than j. So a matrix capital A is equal to, see here it's better if you replace with zeros, so you won't get any ambiguity later. So you can say 0, 0, 0. Okay, so see here, a matrix A is equal to Aij n by n is said to be, for all I less than j, correct? Okay, all of you are correct. So see here, the matrix A is equal to Aij n by n is said to be a lower triangular matrix, is said to be a lower triangular matrix if Aij is equal to 0 for all I less than j. Okay, in bracket you can write all upper diagonal elements are zeros. All upper diagonal elements are zeros. Correct? Yeah, of course, all of you are correct. Example, if you want me to write an example, we can write A11 0 0, A21 A22 0, A31, A32 and A33. Look, I am never talking about lower diagonal elements when I am discussing about lower triangular matrix. Okay, my only intention is these three should be 0. They can be 0 or non-zero, doesn't matter. Okay. Okay, so I'm moving for the next part. Taken this? Okay, so next, fourth type, diagonal matrix. Diagonal matrix. Now, tell me what is a diagonal matrix? All of you, tell me what is a diagonal matrix? Only principal diagonal elements are non-zeros. That's not the correct way of defining pair. All the non-diagonal elements should be zeros. Okay, elements only in diagonal. See, I'm telling you, whenever I'm talking about upper triangular matrix, okay, so see here, I am talking only about these three elements. Okay, I am talking only about this triangle, but I am not talking about any of this. Okay, so the correct way of defining this is only lower diagonal elements are zeros. So when I ask you what is about this diagonal matrix, you should say all non-diagonal elements should be 0. Livia, that's what I told you. Diagonal elements can also be 0, no issues. But you should have all non-diagonal elements are zeros. Correct, Neeraja? So see here, a matrix A is equal to Aij n by n is said to be a diagonal matrix. Is said to be a diagonal matrix if Aij is equal to 0 for all I not equal to j. Okay, so basically if you see, yeah, all of you are correct. So see here, so basically if you see, diagonal matrix is a combination of upper triangular matrix plus lower triangular matrix. Means Aij is equal to 0 for all I less than j, and Aij is also 0 for all I greater than j as well, which means except in the case I is equal to j, in the remaining all cases this Aij means the element within the matrix is 0. That's what I have stated here. Actually, I mean combination of these two conditions is nothing but this condition I not equal to j. Okay, so see here. Examples: A11 0 0 0, A22 0 0 0, A33. Okay, see the values of A11 A22 can also be zeros, no issues. Okay, I just want to tell you that the elements other than the principal diagonal elements are zeros. Okay, so please, yeah, diagonal elements can also be 0. That's what I told you, because I didn't talk anything about diagonal elements here. Okay, I only talked about non-diagonal elements. So let us write in a neat way: 0 0 0, A22 0 0 0, A33. Okay, now fifth type, scalar matrix. What is a scalar matrix? All of you, please tell me what is a scalar matrix? Aij is equal to constant for all I is equal to j, and along with that we can say something, a diagonal matrix. Okay, else you can write a matrix A is equal to Aij n by n is said to be a scalar matrix, is said to be a scalar matrix if Aij is equal to some constant for all I is equal to j, 0 for all I not equal to j. Means if you write this, the matrix could look something like this: A is equal to K 0 0. If I'm talking about n value of the particularly 0 K 0 0 0 K. This is how you'll be getting a 3 by 3 scalar matrix. Okay. So in a scalar matrix, now we have special cases. If K is equal to 1, then the scalar matrix is called identity matrix. Identity matrix. If K is equal to 0, then the scalar matrix is called null matrix. Yes, null matrix. Okay, so if you talk about identity matrices, identity matrix is of the form 1 0 0 0 1 0 and 0 0 1. Of course, I am writing only 3 by 3s. And yes, null matrix is equal to 0 0 0 0 0 0 and 0 0 0 as well. This is of size 3 by 3. Okay, so now we have different kinds of matrices with corresponding value of K. Okay, so next we'll define something called transpose of a matrix. Transpose of a matrix. Now tell me, what's the transpose of a matrix? Do you have any knowledge on that? What is transpose of a matrix? Interchanging rows and columns, correct? So for a matrix A is equal to Aij m by n. For a matrix A equal to Aij m by n, we say that the matrix B where B is equal to Bij n by m as transpose of A if Aij is equal to Bji for all I comma j. Yes, unit matrix. Correct. Unit matrix is also called that. Okay, so means basically if you see the elements like this, if you have example A is equal to A11, A12, A21, A22. Let me add one more, A13, A23. If you see the size of this matrix is 2 by 3. Then if B is equal to a matrix of size 3 by 2 such that Aij is equal to Bji, means here the first row first column should be same as the first row first column here. Then if you have some matrix like B11, B12, B21, B22, B31 and B32, this matrix should be same as A11, A21, A12, A22, A13 and A23, and these two matrices should be same. Okay. And of course, this is also of size 3 by 2. Then you see B11 is same as A11, B12 is same as A21, B21 is same as A12. Means generally if there is Ij, this gets interchange here. So if Aij is equal to Bji or Aji is same as Bij, then we say the matrix is transpose of the actual given matrix. It is denoted by B is equal to A transpose with a T on the superscript of A. Okay, so B is equal to A transpose. We read this as A transpose. B is equal to A transpose. Okay, so if you see this is how generally we denote the transpose of a matrix. Clear? What's a transpose? Now, if that is clear for us, we'll look at something called symmetric matrix. Symmetric matrix. Okay, so right here, a matrix A is equal to Aij n by n is said to be a symmetric matrix. A transpose is equal to A. Okay, is said to be a symmetric matrix if Aij is equal to Aji for all 1 less than or equal to I comma j less than or equal to n. Means generally it denotes A transpose is equal to EA. This should happen. Okay, and mathematically this is the condition for the matrix to be symmetric. Example, if you take for example, A is equal to 1 4 3 4 2 1 and then finally 3 1 4. So if you see, if you transpose this matrix, again you'll be getting same matrix. Correct? We have, if you want to connect, we have A transpose is equal to, if you interchange this column as first row, we have 1 4 3 again. For this we have 4 2 1 again, and for this we have 3 1 4. And if you see, both the matrices A and A transpose are same. Okay. But these conditions are generally important because in exam they will be asking you these conditions. Okay. 7. Skew-symmetric matrix. Can you tell me what is a skew-symmetric matrix? All of you, can you tell me what is a skew-symmetric matrix? A transpose is minus A, correct? So a matrix A is equal to Aij n by n is said to be a skew-symmetric matrix. Is said to be a skew-symmetric matrix if Aij is equal to minus Aji. Did someone know this condition? No. Okay, A transpose is equal to minus A. Happy with that? Okay, fine. So Aji is equal to minus Aij or Aij is equal to minus Aji for all 1 less than or equal to I comma j less than or equal to n. As you told, A transpose is same as minus A. Okay, so can you give me one example? Can some of you give me one example for that? Some normal case, like 2 by 2 case could be fine. Write elements A11, A12, A13, A14 in the box. Okay, in the comment box. Right, first or first column element, first or second column element, second or first column element, and second or second column element. And tell me give one example to me. Mauli, correct. Okay. 1, 2, minus 2, 3. No, let me tell you something. Note, you can write one note here if you would like to write. The principal diagonal elements of a skew-symmetric matrix are 0. The principal diagonal elements okay, last problem with lower diagonal elements negatives, but that's not the correct answer. See here, the principal diagonal elements of a skew-symmetric matrix are 0. Of a skew-symmetric matrix are okay, not are 0, because see, we have Aij is equal to minus Aji, correct? For all 1 less than or equal to I comma j less than or equal to n. Yes or no? So now see here, if element is on principal diagonal, if element is on principal diagonal, this implies I is equal to j, correct? So if you put I is equal to j here, Aii should be equal to minus Aii, which means 2 times of Aii is equal to 0. So this means Aii is equal to 0. So if the element is on principal diagonal, definitely the value should be 0. Clear? Let us see whether we are getting the things or not. Example. A 0, 1, 2, minus 1, 0, 4, and minus 2, minus 4, 0. So if you take this matrix, this is a skew-symmetric matrix, correct? Because if you take A transpose of this matrix, look, if you transpose this column as a row, you have 0, minus 1, minus 2. Second column, if you transpose as second row, 1, 0, minus 4. And third column, if you transpose as third row, 2, 4, 0. So if you take minus A transpose, you have 0, 1, 2, 1, okay, minus 1, 0, 4, minus 2, minus 4, 0. And if you see, this matrix is same as matrix A, correct? See, let us suppose I have put some number here instead of 0. Let us suppose I have put 3 here. Then this value is also 3. Then at this point I will be getting minus 3. And if you see, this is not equal to A, because in A you don't have a minus sign here, but here you are getting a minus sign. Okay. So generally, if you take some numerical value other than 0 for a principal diagonal element of a skew-symmetric of any matrix, the matrix can't be skew-symmetric. Okay. So the principal diagonal elements of all the skew-symmetric matrix are 0. Okay, clear? Did you all understand why the principal diagonal elements of a skew-symmetric matrix has to be 0? Understood? Suppose if you take any other number, there comes a minus sign change for one of the elements within the given matrix. Next, second important point is the sum of all the elements. The sum of all the elements of a skew-symmetric matrix the sum of all the elements of a skew-symmetric matrix is 0. Correct? Because if you see, for every Aij, there exists Aji with opposite sign. And principal diagonal elements are already zeros. So sum of principal diagonal elements is 0, and sum of all other elements will also be 0, because for every Aij that exists here, there exists a Jii with negative sign. Correct? So when you add these two, Aij plus Aji is equal to 0. Since Aij plus Aji is equal to 0 for all I comma j, or 1 less than or equal to I comma j less than or equal to n, for your happiness. Okay. Clear? Now see properties of transpose. Just I want to tell you two properties here, since we know what is a transpose. Properties of transpose of a matrix. First property, A plus or minus B, means if you add two matrices or subtract, I mean a matrix from other matrix, then this is equal to A transpose plus or minus B transpose. Second, if you multiply the matrix with some number and if you take the transpose, answer is K into A transpose, because for the scalar K you can't apply this transpose because scalar is just a number. There will be nothing like to interchange rows and columns. Next, AB whole transpose is equal to B transpose into A transpose. I assume you know how to multiply two matrices. If someone have any doubt, you can ask me. No issues, I'll explain you slowly. So do all of you know how to multiply two matrices? If that's fine, we'll move ahead now. Yes? I want all of you to respond. Yes or no? Okay? So, fine. Now, every square matrix can be expressed as sum of a symmetric matrix, and a skew-symmetric matrix. And a skew-symmetric matrix. Okay. Okay, so see here. Skew-symmetric matrix, how? Let A is equal to half times A plus A transpose plus half times A minus A transpose. Can we write this? Because if you are simplifying the things, A plus A transpose by 2 plus A minus A transpose by 2, this plus A transpose and minus A transpose gets cancelled. Okay. So, and again, if U is a skew-symmetric matrix, then definitely U by 2, U by some number is also a skew-symmetric matrix, correct? Because that's just a scalar multiplication to all the integers. So, see here. Let U is equal to A plus A transpose and V is equal to A minus A transpose. Correct? This implies U transpose is equal to A plus A transpose whole transpose and V transpose is equal to A minus A transpose whole transpose. So this implies U transpose is equal to A transpose plus A transpose whole transpose and V transpose is equal to A transpose minus A transpose whole transpose. So this implies U transpose is equal to A transpose plus A, because if you transpose a matrix twice, when you interchange first time rows with columns, you will get the transpose of the matrix, and again if you interchange, you will get the original matrix, and this value is same as U. Yes or no? Because this A transpose plus A is the actual U that you have taken, and matrix addition is commutative. You can add two matrices in any of the order, so this U transpose is same as U. But here this is not the case. V transpose is equal to A transpose minus A. So if you take a minus sign common, you have A minus A transpose, and this is minus V. So V transpose is same as minus V. So this implies U is symmetric and V is skew-symmetric. And V is skew-symmetric. Okay. So if U is symmetric and V is skew-symmetric, I have made this matrix A as summation of a symmetric matrix and a skew-symmetric matrix. Correct? So therefore, A is equal to half A plus A transpose plus half A minus A transpose So if you see this A plus A transpose is symmetric, and this A minus A transpose is skew-symmetric. Okay, so likewise, every matrix can be, written as a sum of symmetric and a skew-symmetric matrix. Okay, so this statement is really important. Did you all understand this? How a matrix can be written as a symmetric summation of a symmetric part and a skew-symmetric part? In GATE 2019 in GATE 2020 examination, this question was asked. If A is decomposed into two matrices, into summation of two matrices, a symmetric matrix and a skew-symmetric matrix, he gave this capital A, he gave this symmetric matrix. He asked for this skew-symmetric matrix. Okay. Clear? Did you all understand this? Did you all understand how a square matrix can be expressed as sum of symmetric and a skew-symmetric matrix? Clear? Okay. If you want to use any other number than 1 by 2, here you need to change it, because a by 2 plus a by 2 will give a. Okay, if you want to change number here, you can change number here. Next, multiplication of matrices. Multiplication of matrices. Because I want to tell you something about multiplication of matrices, so that we can deal some other types of matrices now, if you know multiplication of matrices. Okay, so if A is equal to Aij m by n and B is equal to Bij P by Q, then for the matrix multiplication AB, then for the matrix multiplication, then the matrix multiplication AB to be possible, n should be equal to P. Means number of columns in first matrix should be equal to number of rows of second matrix. Correct, Monica? So see here. Example, if you want to write one example for this, A is equal to A11, A12, A21, A22. So this is a 2 by 2 matrix. Let us take B as B11, B12, B13, then B21, B22, B23. So if you see, this is a matrix of size 2 by 3. Okay, so now if you multiply these two matrices, A, B, you can write here, and the order of AB is, AB m by q. Okay, so if you see, no, m by q, because see here, yes, it's not P, Monica, it's Q. So it's, if you now multiply these two matrices, you should get a 2 by 3 matrix. Let us see how we'll get. So one 2 by 3 matrix you should get. See here. For getting the first row, first column element, multiply the first row with the first column. Okay. So A11 into B11 plus A12 into B21. This is the first row, first column element. Now to get first row, second column element, multiply first row with second column. So A11 B12 plus A12 B22. Okay. Next, to get first row, third column element, multiply first row with third column. So if you multiply that, A11 B13 plus A12 B23. Next, to get second row, first column element, multiply second row with first column. So if you do that, A21 B11 plus A22 B21. Next, Second row, second column. A21 B12 plus A22 B22. Second row, third column. A21 B13 plus A22 B23. So this is how you generally carry out multiplication for this particular matrix. Means if you want ith or jth column in the product matrix, you should multiply ith of the first matrix. I mean, this is called actually prefactor in this AB. This A is called prefactor and this B is called post factor. Okay, by names. So see here, if you want ith or jth column element in this product matrix, you should multiply the ith of the prefactor with the jth column of the post factor. Okay. Next. Matrix multiplication need not be commutative. Matrix multiplication need not be commutative. Means AB may or may not be equal to BA. See, if for example, if A is of order 2 by 2 and B is of order 2 by 3, then you will get some matrix of order 2 by 3 when you multiply. But if you want to multiply B is of order 2 by 3 and A is of order 2 by 2, and if you see, this multiplication is not possible. When number of columns in first matrix is not equal to number of rows in second matrix, this implies AB does not exist. Correct? If AB does not exist, then we can't talk about equality. Yes or no? So if both the matrices are of different sizes, then sometimes AB may not be equal to BA. So matrix multiplication need not be commutative. Next. Matrix multiplication is associative. Associative means, for example, if you have three matrices A, B, C, then if you product BC first and then if you multiply with A, or if you multiply AB first or then if you multiply with C, answers doesn't change. They remain same. Okay, so answers doesn't change in such cases where A of BC is same as AB of C. Next, you can write matrix multiplication is distributive. Matrix multiplication is distributive. Means if you have A into B plus C, then you can write AB plus AC. See, you can't write BA plus CA. Why? Because matrix multiplication need not be commutative. Okay. It's already 1 hour since we started. Time is 11:30. Okay. We'll go fast. Okay. Oh, okay. We'll go slow. No problem. Fine. Can I move ahead? Okay, I'll give you some time. Please take notes. Just a minute. I'll be back. Please take these notes once. Okay? Don't worry about okay, clear? Taken this? Did you take the notes for this? If once it's finished, please say yes. We'll move ahead. Okay. Yes? Okay, fine. Okay. So we'll continue with the types of matrices. Previously, how many types we have talked about? It got hanged. Okay. So if you see, we have talked about some 7 kinds of matrices. Now let us start with this. 8. Orthogonal matrix. Orthogonal matrix. What is orthogonal matrix? Does someone have any idea regarding this? A into A transpose is I. Okay. A matrix A is said to be orthogonal matrix. Is said to be orthogonal matrix if A into A transpose is same as A transpose into A is same as I, where I is identity matrix. You can write I is identity matrix. Okay. Example: A is equal to cos theta minus sin theta 0, sin theta cos theta 0 and 0 0 1. Okay, so this is one such good example of orthogonal matrix. So if you multiply this A into A transpose, see what we have: cos theta minus sin theta 0, sin theta cos theta 0 0 0 1. If you multiply this with the transpose of this, look, this first column I am writing it as first row cos theta sin theta 0. This second column I am writing it as second row minus sin theta cos theta 0, and third row is finally 0 0 1. So if you multiply these two matrices, see, cos theta into cos theta is cos square theta, plus minus sin theta into minus sin theta is sin square theta. So cos square theta plus sin square theta, we have 1. Next, cos theta into sin theta minus sin theta into cos theta, it is 0. Then 0 into cos theta plus 0 into minus sin theta plus 0 into 1, answer is 0. Next, sin theta into cos theta minus sin theta into cos theta, this value is 0. But if you multiply second row with second column, you will get 1. Again, this is 0. And finally 0 0 1. Please check whether you are getting this or not. Please check this. Yes, getting this? 1 0 0 0 1 0 and 0 0 1. So this is one such good case of an orthogonal matrix. In GET examination, they'll put different values here. Like for example, if they put theta is equal to 60 in this matrix, whatever may be the value of theta, this value is always identity matrix. But in exam, to waste your time, they'll be putting theta is equal to 60 degrees, so 1 by 2 minus root 3 by 2, root 3 by 2, such elements will be there. So your time, you need to spend some time over there. I want to tell you one good point here actually, so you can always write this. The determinant of an orthogonal matrix is plus or minus 1. I'll show you why when I'm telling you properties of determinants. The determinant can be plus or minus 1. Okay. So we'll move to the next part. 9. Involutory matrix. A matrix capital A is said to be an involutory matrix. An involutory matrix if A square is equal to I. Example, A is equal to something like 4 minus 1, 15 minus 4. I think this could work out. So please try this. If you calculate A square is equal to A into A. So 4 minus 1, 15 minus 4. And 4 minus 1, 15 minus 4. So if you calculate this value, 4 4s are 16 minus 15. 1 minus 4 plus 4. 0. 60 minus 60. 0 minus 15 plus 16. 1. Okay. So there are some matrices. Yeah, you will be getting I Mauli. So if there are some matrices which when you multiply the matrix to itself, you will be getting an identity matrix. Next. Okay, so next, idempotent matrix. Yeah, you can write A is equal to A inverse for this. And for orthogonal matrix, A inverse is nothing but A transpose. Since I didn't talk about inverse and all, I am not talking that particular words here. So idempotent matrix. A matrix capital A is said to be idempotent matrix if A square is equal to A. Example, A is equal to 4 minus 1, 12 minus 3. Try to calculate this value. Try to calculate A square for this. A square is equal to 4 minus 1, 12 minus 3 into 4 minus 1, 12 minus 3. (16 minus 12). 4 minus 4 plus 3 minus 1. 48 minus 36. 12 minus 12 plus 9 minus 3. Okay. Clear? So if A square is equal to A, identity matrix is always one such good example of this. You can write 1 0 0 1 and you can calculate A square. How many times you multiply identity matrix doesn't matter, you will get identity matrix. Clear? Can I move ahead? Is it okay to all of you till this moment? People are online. See, if A square is equal to A, then A power n will also be equal to A generally. Okay. Yeah, other powers. Next, nilpotent matrix. What's the number, by the way? 11. Correct? Nilpotent matrix. Now let us see what is this nilpotent matrix. A non-zero matrix, capital A, is said to be a nilpotent matrix is said to be a nilpotent matrix if there exist n belongs to natural numbers such that a power n is equal to 0 matrix. Generally, null matrix is denoted by 0. Okay, so a power n is equal to 0, and the smallest possible n is called index of the nilpotent matrix. Index of the nilpotent matrix. Okay, for example, if you take things like 2 minus 1, 4 minus 2, then this implies, okay, let us suppose this is A. This implies A square is equal to 2 minus 1, 4 minus 2 into 2 minus 1, 4 minus 2. So now if you calculate this product, 2 2s are 4, 4 minus 4, 0. Minus 2 plus 2, 0. 8 minus 8, 0. Minus 4 plus 4, 0. So if you see, even Suresh, I think you are most worried about the completion of syllabus. Okay, in the morning class you asked me when will you start matrices, and now you are starting asking when will I complete syllabus. Okay, it may take, actually as per my plan, June 29 is the last day where we complete the syllabus of mathematics. Okay, so a square is equal to nilpotent matrix. So index is equal to 2 for this nilpotent matrix. Okay. Clear? Taken? No, period is 1, index is 2, Molly. Clear? Taken? Now, I think it's better if you solve a problem now. The sum of all the elements of the matrix A is equal to Aij m by n, where Aij is equal to I plus j for all 1 less than or equal to m less than, I less than or equal to m, and 1 less than or equal to j less than or equal to n. So basically this is an m by n matrix, so that's why we denote rows are changing from 1 to m and columns are changing from 1 to n, and each element is specified by A is equal to I plus j. So please try and tell me the answer. Just I want you to write the matrix, count all the elements and tell me. That's it. Very simple question. So please try to solve. I'll be giving you some time. Let us see. So Vijay, this question was asked different times in GATE examination with different values of m and n. This aij is I plus j, but Lokesh, I didn't give you the values of m and n, correct? So how can you tell me 45? Your answer should be in terms of m and n because I didn't give you the values of m and n here. It's already 1 minute. Okay, still no problem. In GATE exam, you have 2 minutes 55 seconds time for each question, so I can work out. Mn is the wrong answer. You haven't some 30 on live, but very few could answer this. Okay. Last 15 seconds, if you want to try. M and P. What is P? Nagsai. Okay, we crossed 2 minutes, so let me help you out. See here. A is equal to A m by n, of course, is equal to, all of you, please stop writing and see here. What could be the first element? A11 is 1 plus 1, correct? 1 plus 1. First or second column element is 1 plus 2. First or third column 1 plus 3 and so on. Finally, since we have n columns, this element is 1 plus n. Correct? Second row elements 2 plus 1, 2 plus 2, 2 plus 3 and so on, 2 plus n. Similarly, 3 plus 1, 3 plus 2, 3 plus 3 and so on, 3 plus n. Wrong Suma? Wrong Ajay? So if you go on like this, finally you have m to. So this is m plus 2, m plus 3 and so on. You will be getting m plus n. Now from here see carefully. Okay. M plus n into n plus 1 by 2. I think that could be reasonably correct. Okay, let us see what happens. So now this is the matrix that you want, correct? And these are the elements inside the matrix, and you want the counting summation of all these elements. Look here. Now here you have one here, second one, third one, and so on, nth one. So finally, how many ones you have in the first row? Ones. How many ones you have in the first row? In one is there in every term. So n times there is 1. So n plus, yes, correct, n plus 1 plus 2 plus 3 plus 4 and so on plus n, which is sum of first n natural numbers, n into n plus 1 by 2. Correct? So this is sum of all the elements in the first row because you have n ones plus sum of first n natural numbers. So this is sum of all the elements in the first row. Now coming to the second row, you have 1, 2, second 2, third 2, and finally nth 2. So sum of all these 2's is 2n plus. Again, you have sum of first n natural numbers as the second term of the summation. So n into n plus 1 by 2. And so on. If you come here, finally for the last term, you have m. Like this, you will be having n times of this m. So mn plus 1 plus 2 plus 3 and so on plus n, which is n into n plus 1 by 2. So now if you add all these expressions, that is nothing but sum, correct? So now let us try to add all these expressions. See, n into n plus 1 by 2, n into n plus 1 by 2 and so on, n into n plus 1 by 2. See, if you see, this n into n plus 1 by 2 is present in every term. So what is the summation of all these n into n plus 1 by 2's? there are total m times of this n into n plus 1 by 2. So m times of n into n plus 1 by 2 plus n plus 2n plus 3n and so on plus mn. So if I take one n common, I have 1 plus 2 plus 3 plus and so on plus m. So if you see m into n plus 1 by 2 plus n into, this is sum of first m natural numbers. So m into m plus 1 by 2. So if you take mn by 2 common in both the terms, m plus n plus 2. Correct. So this is summation of all the elements in this matrix. Mn by 2 into m plus n plus 2. Okay. So now what are the values they give for m and n? You can substitute in this expression. But this question was asked a lot of times in GATE exam with the different values of m and n. Okay. Okay, so next. If you have any doubt anywhere in this, you can ask me. If everything is clear, please say yes. We'll go for the next question. Okay, so I'm going for the next question. If A is equal to Aij 5 by 5, where Aij is equal to I square minus j square for all 1 less than or equal to I comma j less than or equal to 5, then the sum of all the elements of matrix A is dash. Yes, Avanish Singh, this classes are for mechanical as well, because in mechanical GATE syllabus you have this linear algebra. Okay, so you do attend. So please try this. Zero, because given Aij is equal to I power 5 minus, okay, I square minus j square. Then what about Aji? J square minus I square, correct? So if you take one minus sign common, you have I square minus j square. Okay, so this is minus Aij. So this implies Aij is equal to minus Aji. What does this condition tells us? This condition tells us matrix is skew-symmetric. Correct. If matrix is skew-symmetric, what is the sum of all the elements of the skew-symmetric matrix? 0. We have seen. Correct. Okay. So generally, when you see I power n minus j power n format, the matrix is skew-symmetric, undoubtedly. Okay. Clear to all of you why this is 0? Very simple. Explain once. Yes, that's why I asked you. So this given Aij is of this form, correct? So if you want Aji, means see, when there is Aij, you have I square minus j square. So now when you have Aji, you will have j square minus I square, because here there is j in place of I and I in place of j. So these two get interchanged, a square minus I square. So if you take one minus sign common, this AJI is same as minus AIJ. And if you remember a bit about this, we are talking about this. See here, the sum of all the elements of a skew-symmetric matrix is 0. And for skew-symmetric matrix, I told you AJI is same as minus AJI. I mean AIJ is same as minus AJI. So this is satisfying that condition, the element of this format. Okay, clear Vijay Sai? Now can you go for the next question? Class is up to 12:30. Yeah, I feel, but can we end it at 12? How many of you are okay with 12? Raise your hands in the comment box, or you can put a smiley. That could be good. (12 or 12:30? If 12, put a smiley in the box, or else some hand. Smiley, okay. Fine. We'll end at 12 o'clock for today. No issues. We'll extend the things. Okay. Fine. So see here. Next. So now that we have seen some good examples of idempotent matrix, then nilpotent matrix and involutive matrix and all these things. Correct? So now we'll talk about something that's really important. The number of operations or the number of multiplications, for example. Required, the number of multiplications required to calculate the product of two matrices, A 3/4 and B 4/5 is dash. $60. Correct, Suma. 60. See, generally these kind of questions come in GATE exam with different numbers of m by n and n by p. So let me tell you something. If the matrices A m by n and B n by p are to be multiplied, then the total number of multiplications required is, any guess, m into n into p, because see, I will tell you. Let us suppose A11, A12, A21, A22 is there, and this is a 2/2 matrix, and B11, B12, B13, B21, B22, B23. Let us suppose these are two matrices, and you need to multiply these two matrices. Look, for getting total, you will be getting this order as 2/3, and 2/3 means you have 6 elements. Correct? So now let us see how many multiplications you need to perform to get the first element of the product matrix. For getting the first element of the product matrix, you need to multiply this row with this column. Correct? So for getting the first element in the product matrix, you need to multiply this element with this element. So one multiplication plus again this element into this element. So two multiplications you need to perform for getting one element here. So on. So similarly, if you for one element, if you want two multiplications, similarly there are 6 elements totally. So for each element, two multiplications will total give you m n p multiplications in general. Okay. Next, total number of additions. Total number of additions required is, any guess? M into n minus 1 into p, correct. Okay, m into n minus 1 into p. So if you look at this question now, 3 into 4 into 5 is 60 is the answer. Yeah, for this case, it's 3 is a 9, 9 5 is a 45 additions you will be getting. If they ask you total number of additions required, if that's the question, then 45 would be the answer. Okay, but actually this property is really important. That could be some time saving for you in exams. Okay, so next, so it's already 12 o'clock. Okay, 11:59. So we have some more time, 1 minute. We'll write something. Okay, so if you see this, we came to know that m and p is the number of multiplications that are required, and m into n minus 1 into p is the number of additions that are required. Now if you see, the minimum number of multiplications required to evaluate the product of the matrices, yeah, that's what I'm dealing now. So to evaluate the product of the matrices A 3 by 4, B 4 by 5, and C 5 by 3. So if you want to evaluate this product, there are two possibilities. You can multiply AB and then you can multiply C with the product of AB, or you can multiply BC and then you can multiply A with the product of BC. Correct? So these are two cases. So now tell me, what are the number of multiplications minimum required? $45 again, 36, 180, getting different answers. See, let me help you. Or else should I give some more time? 105, Mauli? Let me check. See, first of all, you have two possibilities. You can multiply AB and then you can multiply C for that, or you can multiply A to the product of BC. Correct? Look, the order of this AB is 3 by 5, because you know this is 3 by 4 and this is 4 by 5. So if you multiply, you will be getting 3 by 5, and to this you will multiply 5 by 3. Similarly, here A is 3 by 4 and BC could be something like 4 by 3. Now see here, to calculate AB, you need how many multiplications? Look, A is of order 3 by 4 and B is of order 4 by 5. Okay, so many are writing now 105. Let me check. So AB, if you want to evaluate this product, number of multiplications required is 3 4s are 12, 12 5s are 60. So total multiplications you need is 60 to get this product AB. Similarly, to get this product BC here, how many multiplications you need? 4 5s are 20, 20 3s are 60. Okay, 4 5s are 20, 20 3s are 60. Okay, fine. Next, If you multiply AB with C now, this is of order 3 by 5 and this is of order 5 by 3. So if you see number of multiplications required to for this particular step, 3 5s are 15, 15 these are 45. So total 105 multiplications here. Because while calculating AB, you need to have 60 multiplications, and when calculating ABC, you have 45 multiplications. Now, if you are multiplying this A with BC, how many multiplications you need? This is 3 by 4 and this is 4 by 3. So 3 4s are 12, 12 3s are 36. So total 96 multiplications you need here in this case. Okay, so here you need 105 multiplications and here you need 96 multiplications. So the minimum 84. How come? Okay. So see here. So the minimum number of multiplications that you need is 96. Okay. Generally, this logics we will use in coding. Okay, because if number of operations increases, the execution time of the program increases. Correct? Normally. So before straight away giving the code, we'll determine which two matrices to multiply first. If you see here, 96 operations is sufficient, but here 105. So if you see nearly some 9 operations are different here, so we can save some time by performing. Of course, this is a smaller case, but when we are multiplying some big matrices of size 100 by 100 while you're coding and all, I myself used I need to one time there came a necessity in my exam where I need to solve 196 by 196 matrix. Okay, because there are a lot of variables when you deal with physics that's happening. So in such cases, when writing codings and all, it takes a lot of time to write the coefficient matrix itself. I mean, we'll see what is coefficient matrix and all. But generally, for putting a constraint on the number of operations and to save time, we need to check such things before writing the code. Okay. So I hope we had enough of class today for 2 long hours in the morning and now around some 1 hour 35 minutes. So is that okay? Is it understandable to all of you? But this matrices is somewhat important because every year some 2 to 3 marks comes from this. If you are okay with this, you can say yes, we'll wind up this session. If you have some difficulty, you can talk to me, or else you can say yes in the comment box. I want all of you to respond. See, nearly some 42 are online. So please respond if you are okay with this. Vijay Sai, you can ask me personally. I gave you my contact, so you can talk to me. Still, how many chapters remaining? Apart, excluding this linear algebra, we have probability and statistics and numerical methods. That's it. And some transform theory for some individual groups. Okay then. Okay then, fine. Have a nice day. Thank you all.